So these are just different concentration units we end up dealing with when we, for different situations in chemistry. In physics we use some of these different ones, AP Chem, biology especially. Loves to use molarity and loves to use percent by mass. Mole fractions used a lot of times in kinetics and like how fast a reaction's happening and equilibrium, things like that. So we're going to be using all of these different things for different parts of the course. You just have to be able to convert between them. So the best thing I can do with this is to do a problem with you. So you need a calculator on your desk and you need a periodic table right now. What we're going to do is we're going to write down the givens, just like we used to do from the beginning of the year when we did dimensional analysis. Because all this is a dimensional analysis problem while fitting everything, all the pieces together.
I forgot to put on the
So on this first problem, they gave us some stuff. What did they give us?
They gave us 28 grams of glucose.
That's an ounce.
So I'm keeping these equations up on the board, by the way, so I can use. So they told us what?
It's 28 grams of glucose.
28.0 grams of C6H12O6.
Yes, sir.
Told us that. Did they tell us the molar mass of that?
No.
No, but we could if we wanted to, right?
Yeah.
So, and then they told us how much water?
350.
50 grams of H2O. Do you know the molar mass of water?
18.02.
18.02. You remember that from hydrates and stuff, right? What else did they tell us?
The final volume of the solution is
Yeah.
384 milliliters.
The volume of solution is, what is it?
384 milliliters.
4 milliliters. And water, by the way, its density is about 1 gram per milliliter, so that's about 350 milliliters of water plus about whatever the difference is of the glucose. Glucose has a different density, so that's why it's a little different than the 28. So what we need to do here is, you see we have a bunch of different units in all of these different ones. If I want to solve for all of these from this information, I can, but I don't have all these units, right? So the first thing I need grams. Well, I've got grams. I need moles. How can I get to moles of these different things?
You divide.
Molar mass, and it will be division. Yeah. So what's the molar mass of C6H12O6? Can somebody do that real quick in their calculator? 12.01 times 6, 1.01 times 12, 16 times 6. Then add them all together. So it's 100 something, maybe?
180.18.
180.18. Anybody want to confirm that?
Yeah, 180.
180.18.
Sweet. So we've got the molar mass of both. We've got the mass of both. Let's do some math. This is where the actual problem starts. Look, I'm not actually solving for any of these yet. I'm just pulling out and trying to get as much information from what I've been given, right? So I'm going to take 28.0 grams of C6H12O6. I'm going to separate the information. And if I have grams up here, where should the molar mass go?
Bottom.
Should go on the bottom, right? So 180.18, 1 mole, and you can put it in the calculator, right? You're going to do the same thing with the water. 350 grams H2O, 18.02 grams, 1 mole. You're going to do the same thing. And the reason you're doing the same thing is because eventually you're going to need moles of all these different parts. You're going to need grams of all these different parts. You're going to need liters of all these different parts, right? And you might as well go ahead and get that information. So do this in your calculator. Should be a decimal for the top one. Don't round. 1554.
1554.
Yeah, we do not want to take and round here, because if we round here, it could actually mess up things later on. So that's our moles. You see how I'm labeling with the unit and the compound? You should do that. Okay, do the water now.
19.42286349.
So 42286 349. Okay. So we've got moles of everything. We've got grams of everything. So I can get moles. What? By the way, what is solute? Do you remember what that is?
It's what's being dissolved.
It's what's being dissolved. So looking at this situation, what's probably being dissolved?
The sugar.
The sugar, because there's less of it. Solute is always in lesser amount than the solvent. So that kind of will help you. If they're equal parts, you got to think logically here. Water almost always is the solvent. In most of the problems we do, in the labs that we do, I mean, we just did a lab with water as a solvent, right? So think about that. So I need moles of solute. I've got moles of solute. I need liters of solution. Well, I've got milliliters of solution, don't I?
So you can just multiply by 1,000.
Is it multiplied by 1,000?
Yes.
You're in milliliters. What's the
Divide-
conversion for
divide by-
milliliters?
Wait, it's
Oh,
1 liter is 1,000 milliliters.
Yeah, so for every
Yeah.
1 liter, it's 1,000 milliliters. You gotta be careful. Don't try to do it in your head. Don't try to move decimal points. Think back to August, right? When we did dimensional analysis straight. There's 1,000 millis for every 1 base, right? So if 1,000 goes on the bottom, so you're gonna end up 0.384, not m, liters. And this is solution. They told us it was a solution, so I'll label it solution with apostrophe, because I'm lazy and don't want to write it out. Okay? Everybody have that? So I have liters solution. I could find molarity right now if I wanted to, right?
Yeah.
I'm gonna keep going, just make sure I have everything. Moles of solute, kilograms solvent. Well, I don't have kilograms of salt. I don't have any kilograms up here, do I?
It's just
You just
0.3.
multiply.
It's
divide it by
0.35.
1,000. No,
Yeah. So
divide.
I know the solvent's water, right? So I know I have 350 grams of water
Just divide to 1,000.
Divide by 1,000.
divided by 1,000, because for every 1,000 base units, you have 1 kilogram, right?
Yeah.
This is on the backside of your periodic table. Remember that?
Yep.
Seth, I know you're new here. You have that on the bottom part. Your teacher probably at your other school had that. At the bottom, it has all the different base unit conversions, metrics. You can use that. That's on the test, so you can have that. So that gets you 0.350 kilograms of the solvent. So that gets me to kilograms. That's great. I've got moles of everything. So this is called the mole fraction. It's literally all moles. We've got that now. Gram solute, gram solution. I've got liters solution. I don't have liters of solute, but let's look at the problem. Did they ask me for percent by volume?
No.
No, they just asked me for percent by mass, so I don't need this stuff over here. Okay? So I've got everything I need to do. So just pick one and start with it. Which one do you want to do first?
Molarity.
Molarity, because you've done it before. I mean, I usually do molarity first. So we're going to do molarity is moles of solute over liter solution. I always rewrite the equation and then put it in. So mole solute is the 0.155401554. Liters is 0.384 liters. Right? And then you hit the equal sign.
0.404687947.
And then it's a big M, right? Because it's polarity. So sig fig wise, I think they gave us 333, so we'll just take 0.405. 0.405. And then glucose, C6H12. So that's the molarity of glucose in the water. You did that last unit, that should feel pretty fresh, right? What do you want to do next? Your call. Molality, yeah, I like to just go down the list, but it's your call. You can do whatever you want. So molality is little m. It's moles of solute per kilogram of solvent. The reason we have two different units that are very similar is molarity deals with volume. Well, what if you have something that with heat changes volume, right? There's certain liquids that when you heat them up, they start to change volume, and that messes up all the molarity, because if you're changing volume, you're changing molarity, right? By using the mass of the solvent, it doesn't matter if it's expanding or not. It has the same weight during the heating process. So that's why sometimes we use that. Still the same top, 0.15540015554. It's just now got kilograms, so 0.350 kilograms. So what do you get there?
0.444000444.
So 0.444, and it's a little m, C6H12O6. I'm running out of space. Not sure if the camera will get this, but we'll try. What do you want to do next? Mole fraction?
I think you've got.
Percent by mass.
You want to do percent by mass? It doesn't matter. So we'll do percent by mass. So percent by mass. So percent by, sometimes it's labeled M over M, mass over mass. Sometimes it's G over G, right? So it's the mass, so it's 28 28.0 grams of the glucose over 28.0 grams plus 350 grams of water times 100. What a lot of people do wrong on this problem is you'll put in your calculator 28.0 divided by 28.0 plus 350, and because your calculator's dumb, it'll divide these two and it'll be 1 plus 350. So you'll get like 3,000 something percent, right? Parentheses on the bottom, and it'll be your friend. Right, just like when we did percent error. A lot of you guys messed up percent error when we did that stuff too. So what do you get here?
7.734.
7.734, so 7.73%.
Yeah.
Is that? Good there. And now mole fraction. Let's try to add it right here. So mole fraction is 0.155. This one's the longer one because of all the calculated stuff. Over 0.155400155 plus 19.4228639. Again, parentheses. These are both moles. I just didn't write the units because I was running out of space. Right? It's a lot of work, isn't it? Right? But chemists do this all the time to be able to get between and talk to each other. Right? There's even environmentalists use parts per million. You probably heard of that if you've ever read an economic study or an environmental study about the ozone layer or CO2 emissions. Parts per million or parts per billion, ppb, ppm is a lot of times used. It's all math to get between, and different scientists use different units depending on what field they are, what they're dealing with, that kind of stuff. What do you get here?
0.01660301.
0.0166014, and that is the mole fraction of C6H12O6. We label it like that. Great, you have all those different things, right? I didn't label the percent here, but that was the percent of glucose. Mole fraction is nice because when you have fractions of different things, they add up to 1, right? So if I have like males and females, the fraction of males in this room and the fraction of females in this room add up to 1, right? If we did the math there. Here, if I wanted to figure out the mole fraction of water, I could just subtract this from 1 and figure out the mole fraction of water, which is a lot more because you have a lot more water, mole-wise, than the glucose. Does that make sense?
Question.
So that's a full problem. Notice what we did. We started off with what we were given, and we tried to match it to the different types of units that we had and found just the units first, and then we plugged them in. If you use that strategy, it makes this a lot less complicated. I mean, it's a lot of work, but it makes it a little bit more reasonable. Okay? Let's do one more. Somebody give me a time.
9:38.
Yeah, we got plenty of time to do this one then. I'm gonna race at this guy.
A lot of work for one problem.
It is. And most problems are that long. Like, you're not gonna do 4 different things for one problem. You're probably gonna be like, here's the molarity of this and volume. Okay, what is the molality then? So it'll be like 1 to 1. Does that make sense? We're just doing it really long as we're learning and everything. Okay, what is the first thing they gave us here?
He gave us the density.
molar mass of ethylene.
So they gave me the density and the molar mass of ethylene glycol. This is what's in antifreeze. Okay, it's actually what helps your car not freeze in the winter and also not overheat in the summer. Antifreeze does double duty that way. So ethylene glycol has, I'm gonna just label it EG from now on, if that's okay. So the density is, what is it, 114 grams per milliliter. And then the molar mass of ethylene glycol is
62.07.
And they didn't tell us the formula or anything, did they? Of ethylene glycol? It's some carbon compound. It doesn't matter. They gave us molar mass. We can still do the math and stuff that we need. And then they told us the water's density, which I kind of already talked about, right?
It's
1
1
grams per milliliter. And then molar mass is what?
18.02
18.02.
at 20 degrees Celsius.
Yeah, so at the temperature, because it can change, right, with temperature.
That's for molarity, right?
Yeah. Yeah, if it's got that temperature, it won't change that molarity then. And it won't change the density. The densities change. They told us one other thing here. It was in words, though.
The concentration. Wait.
Because we're trying to find all of these, right, this time?
So it's equal one.
They said equal volumes of ethylene glycol and water, right? if it's equal volumes of two different things, what does that mean each one is percentage-wise?
50%.
Each one's 50-50, right? If it's equal volumes, that means they're not different in each other in volume. That means it's 50% one and 50% the other, right? That's a big ticket thing to think about with being able to solve this. Because right now, all of these are conversion factors, aren't they? I can't start with anything here. But if I know percent volume, I might be able to. What they're basically saying is, and what we're going to have to do if it's a volume thing, we're going to need to assume there's 1 liter of solution to do this problem. So anytime where they tell you equal volumes of solution, or they tell you the percent volume, we're going to need to assume that it's 1 liter. If they tell us the percent by mass, we'll probably assume 100 grams to be able to knock out the percentage. Kind of like what we did with the percent composition stuff a few units ago, that kind of thing. We assumed 100 grams for that. Same idea here. So we're going to assume 1 liter, which means that we've got 0.5 liters of ethylene glycol and we've got 0.5 liters of H2O, right? So 50% ethylene glycol and 50% H2O, and this is by volume, and that was the answer to A, isn't it?
Yep.
So we already answered one of the 5 just by reading the problem very carefully. Okay? Now that I assume 1 liter, and now that I have liters, you have densities, don't you?
Mm-hmm.
If you have liters and you have density, what can you find?
The milliliter.
You can find
No. You have density. Like,
So you have volume in liters, and you've got densities that are grams per milliliter.
you can find the mass, percent by mass.
You can find the mass of each one.
Mass, yeah.
Don't look at this. Don't look at this. Right? I can't solve for anything here until I get all my units. Right now, I only have liters of the solution. That's the only one I have right now. I have liters of solute and I have liters of solution. That's the only stuff I have. All the rest I don't have. But if I have liters, so if I have 0.5 liters of ethylene glycol, well, I can use the density to get it to grams, but it's in liters, and this is in milliliters. What do I have to do first?
You have to convert that to liters.
Yeah, so how many milliliters are in a liter?
1,000.
1,000, and so it's for every 1 liter, it's 1,000 milliliters. And then because I've canceled my liters, and I'm in milliliters, I can use the density for ethylene glycol. So it's for every 1 milliliter, it is 1.114 grams of ethylene glycol. You could have done this problem in August, this part of the problem in August. You actually did very similar things with the conversions of knocking them out with density in August, everything. So that can give me grams. Could somebody do that in their calculator real quick? Everything's over 1, so it's pretty easy. What do we get here?
557.
557? 557 grams of ethylene glycol. Does that make sense to everybody with that? We're using density to get from volume to mass, which is what we used to do in August. Do the same thing with water. So 0.5 liters of water that we assumed. 1 liter, 1,000 milliliters, 1.00 grams for every 1 milliliter. So 0.5 times 1,000 is 500. You can do that probably. So great, I've got grams of 2 things. I could do percent by mass right now, couldn't I? I don't like to do that though. I like to just get everything I need. So if I have grams, what can you get now?
Moles.
You can get moles. You can use the molar mass that they gave us, right? So now it starts to click with things. A lot of people forget about density. You know, we did it in August. It pertains to gases, it pertains to liquids, it pertains to a lot of stuff. So if I have grams, so 557 grams of ethylene glycol, what's the molar mass and where am I going to use it? What's the molar mass?
62.
62 that they told us. And where is it going to go?
It's
On
gonna
top.
come
Or no bottom, yeah.
Why bottom?
Because
it's
you wanted
the
to get
molar-
moles,
it's
so you
the
did
Yeah,
the
I want grams to cancel with the 62.07 grams, right? Follow your units. A lot of you guys are still making those mistakes, right? So be careful. Gets you to 1 mole of ethylene glycol. Same thing with the water. 500 grams of water, 18.02, 1 mole of water. And you can get there, right? So calculate that.
8.9737393.
So 973, 73,
93.
93,
27.
27. methylene glycol. This one's probably a lot bigger, like 20 something.
47.478, 4.
Well, I tell you, 27.4694784.
There you go, Trent. Good job. Okay. So we've got the moles of both things. We've got the grams of both things. We've got the liters of both things. We got one thing we're missing. Look at your equations.
Kilogram.
Of which one?
Solvent. which
So
would be
solvent, but they're equal volumes, right?
Yeah, but water is always a solvent. And
Water's,
water
in this case, is probably still going to be our solvent. Even though you have less grams, even though you have equal parts volume, look at the moles.
Yeah.
Right? Water has, you have a whole lot more of the actual water mole-wise, molecule-wise to surround and separate, right? That solvation stuff that we talked about on Tuesday. You've got a lot more of that, and so it's going to be the solvent. So I'm going to use 500
Couldn't have also
grams of water.
labeled the excess reactant? Or not?
Oh, this isn't a reaction. This is dissolving. That's different, right? So for 1,000 grams, it's 1 kilogram. So 0.5 kilograms of, we should label that, water. And so now you've got all your data here, right? The hardest part was this reading, right? When they said equal volumes of each one, and we had to assume the 1 liter. So if it says equal volumes or equal masses, you have to assume 1 liter or assume 100 grams works well for that one too. So just keep that in mind. I mean, you could assume 500 liters and 500 liters if you wanted to. It didn't matter what you assumed as long as they were the same. Okay, they would have worked out. So now put it in. So which one do you want to do first? Your call.
Molarity.
Molarity, sure. So molarity, I'm gonna do it over here a little bit more. So molarity is moles, so 8.973739327 moles of EG. Liters of what?
It's gonna be
Of solution.
So 1 liter of solution.
There you go, 1 liter. So do we even need to put it in the calculator?
No.
No, it's just that number. So I think sig fig wise, they gave us all these in the problem. We'll just do 4 sig figs because all those were 4 sig figs. So 8.7 or 974 molarity. Ethylene glycol. There you go. Molality. Same thing. 8.973739327.
Divided
By what?
by 0.5.
By 0.5, yeah. Kilograms of water. So we're going to divide it by half, basically. So molarity and molality were very different this time. Last time they were pretty close, weren't they? Depends on the temperature, depends on the compounds. I mean, it depends on a lot of different things. Their densities. So what do you get here? It's like 4 point something?
Or 8.
Bless you.
Oh, excuse me. 4.5. 4.5 to. Oh, I guess it should be more, yeah, because it's dividing by 0.5, isn't it? Yeah, you're right. I didn't do math right.
Oh, Trent got it right then.
Oh.
It's 17 point something.
13 point what?
I gotta do
Did
it
Trent
all.
just go up?
God, I just had mental math problem. I'm sorry, guys.
It's
17 point what?
947.
947, so 95.
Yeah.
I don't know.
Molality. Trent, did you get that the first time you put it in? No.
I don't know.
He got 17.
Make sure you type it in. The hard part about this is really just all the numbers. I mean, it's lengthy, isn't it? So you have to make sure you're typing them right. Which one do you want to do next?
Let's just go straight down.
You just want to go next, just straight down. You don't. It doesn't matter. It depends on what you want. So mole fraction is 8.973739327 over the same thing. You see how easy it is to mess up in this just by writing them and typing them in. So be very careful. 27.74694784. Do you get a mole fraction? Right? What time is it right now?
It's 8:50. I mean,
8:50. 9:50. Got plenty of time. We're doing good. Right? So that gets me a number. I don't know what it is. I feel like it's like 0.3 something. 0.2 or 0.3 something like that. Well, 8 divided by 30, no, not, it's really 9. 9 divided by 36 is 0.25, so probably around 0.25. Did you get it?
Does that say 27 on the bottom?
Yeah, 27.74969478.
Zero point 244. That's rounded.
I need one more.
3.
So 2, 4,
2, 4.
Well, it'd be a 4. It'd be another 4.
2,
because
4,
it's
4,
rounded
3.
up.
2, 4, 4, 3. That's the mole fraction of ethylene glycol.
Yep.
Okay. If I wanted the mole fraction of water, what could I do?
You want it? Well, no, you just put the waters on top. Waters
I would.
mole. The amount of moles.
It would be 1 minus mole fraction, right? Because like if there is every 1 out of 5 in here is girls, every 4 out of 5 would be boys. Then. See what I'm saying? Like it would be opposite fractions.
Okay.
That's all mole fraction is. It's a fraction. And then percent by mass. Right, percent mass over mass, then it's going to be the 557 up top, divided by the 557 plus 500. So the solvent, or solute that you're looking for over the solute plus the solvent, times 100 of course, because it's a percentage. So this is going to be something like 50%, 50% or something like that. Put it in your calculators. A lot of people, they'll get through all this and just mess up in the calculator. You don't want to do that.
It's 50.316.
So 3.2.
Yeah.
What's that number on the bottom? Is that 50?
557, just like the 557 up top.
What is the 500?
The 500 came from the solvent, which was water.
Okay, and what's like the sign? Plus sign in between?
Where?
In between the two.
That's a plus, yeah. Because it's solution, right? It's grams of solution. Solution is solute and solvent. It's a good question.
This PowerPoint is on.
It is on Google Classroom. It's 34 to 37. It's posted, right? With the questions. But the hardest part about these questions is reading what they've given you and figuring out all the different numbers. Here's easy. It's plugging it into equations. You're going to be given these on a test. You're not going to have to memorize this. So don't feel like you're stressing out about that. Okay, you're going to have them. The part that you need to get to is all the stuff. I mean, you could have done all of this in August to October, learning moles and learning dimensional analysis, right? It's now just putting them into the right thing. And questions won't be like this on a test situation. Won't be like this in real life. You won't be given this kind of situation and having to find all this. What will happen is they'll tell you, you'll pick up something off the counter at a store and it'll be like percent by mass NaCl in this. And you may need to get it to molarity. And so you'll need to figure this stuff out to get it to moles per liter, right? It just depends on what you're doing, okay? So just keep that in mind, especially when you get to lab situations in the future, you might need that, okay? And you might find that in your research for your PBL, you might find percent by masses for all of your different things and need to convert that. And that's okay. You just need to be able to do that math, okay? That's all the notes I had for the day, was just that practice. Everything. On Monday, we're going to continue with this, just practicing and getting better. Tuesday, we'll add dilutions to it. And then, yeah, that's pretty